Welcome to the 18th lecture of this course. Today we are going to talk about normal forms of context-free grammars, and in particular we will look at this particular normal form known as the Chomsky normal form. Okay. So, this normal form is named after a computer scientist, Noam Chomsky. So, what are normal forms? So, normal forms of context-free grammars are grammars where the production rules have a very specific type of form, or they follow a very specific nature. Okay. So, let me define what Chomsky normal forms are, and we will then talk more about it. So, a context free grammar G equals V sigma P S is said to be in Chomsky normal form, or in short CNF, if first of all every production rule has one of the two types. Okay. So, firstly it can be some A going to BC, okay, where B and C are variables, or it can be some A going to small a, where small a is a terminal symbol. Okay. So, all the production rules are of the following form. So, you either have a variable going to a concatenation of two variables, or a variable going to a terminal. Okay. Well, almost all production rules, there is just one exception, I will come to it. So, this is the first condition, that every production rule has one of the two types. The second is S does not appear on the right hand side of any rule. Okay. So, our start variable, it does not appear on the right hand side of any rule, in the sense that it does not appear on the right hand side. And thirdly, the rule S going to epsilon may be present depending on whether L of G contains epsilon or not. So, the first here is epsilon. So, depending on whether epsilon is contained in L of G or not. Okay. So, if the language of the grammar contains epsilon, then we will have one exception to this rule. So, we will have a production rule of the type S going to epsilon, otherwise we do not have this. So, that is the only exception. So, if a context free grammar has this kind of a form, it is said to be in Chomsky normal form. Okay. So, why are normal forms so important? The reason is, so let me write this as a theorem. Every context free language has a Chomsky normal form grammar. Okay. So, no matter what context free language you take, there is some context free grammar for that language which is in Chomsky normal form. Okay. So, this is a very important thing to say. So, what we will do today is we will prove this, and our proof will again be a constructive proof, in the sense that we will take a context free language and we will take any grammar for that language. It can be any arbitrary grammar, and we will show how to convert that grammar to a grammar in Chomsky normal form. Okay. So, we will show how to convert any arbitrary context free grammar to a grammar in Chomsky normal form. Okay. So, converting a CFG to a CFG in Chomsky normal form. Of course, when we say we convert, it must both the grammars must accept the same language. Okay. So, how do we do? So, this will devise an algorithm, and the algorithm will follow a step by step process. So, the first step is to make sure that the second condition hold, that is, the start variable does not appear on the right hand side of any rule. Okay. So, if appears on the right hand side of any rule, then add a new start variable, say S naught, and add the rule S naught going to S. Okay. So, we first step, if S appears on the right hand side, we add the rule S naught going to S, and this becomes our new start variable. Okay. So, this is removing start variable from the right hand side. The second is removing epsilon transitions. Okay. So, suppose if we have a rule of the form a going to epsilon. Okay. So, suppose in the grammar we have some a going to epsilon, then we remove that rule a going to epsilon, and for every occurrence of a on the right hand side of a rule, we add a new rule by removing that. Okay. So, say that the grammar contains a rule a going to epsilon, then remove a going to epsilon, and for every occurrence of a on the right hand side of any rule remove that occurrence and add a new rule. Okay. So, in addition, let's say that by yeah, so we do this. So now let's look at an example to motivate this. So let's say that we have something like A going to epsilon and B going to U A V, and we have C going to let's say U1 A U2 A U3. Okay. So let's say that we have a grammar where these three rules are present. So then what we do is we first remove A going to epsilon. Okay. So we remove A going to epsilon, and what we do is we have now B going to U A V. We add another rule by removing this occurrence of A. Okay. We do not remove the earlier occurrence, so we keep the earlier occurrence. So we add another rule B going to UV. So earlier we had B going to UAV, now in addition we have B going to UV. Now what about C? Observe that in this rule there are multiple occurrences of A on the right hand side. Okay. So when we have multiple occurrences of A, we will add a new rule for each such occurrence. Okay. So firstly we have the rule C going to U1 A U2 A U3. Okay. Take some space. So first we have C going to U3. Now in addition to this, I remove the first occurrence of A and I get the rule U1 U2 A U3. Now I remove the second occurrence of A to get the rule U1 A U2 U3. Okay. Now I have these two rules again which have a single occurrence of A. So I remove that occurrence of A from these two rules to get a third rule, which is just U1 U2 U3. Okay. So these are the three new rules that I have added from this old rule. So for every occurrence I remove that occurrence to get a new rule. Okay. So this will be the new grammar by removing A. So the third type is removing unit rules. Okay. So if we have something of the form A going to B, okay, what we do is, and let's say we have something like B going to U, okay, so where U is some string, we remove A going to B. Okay, so we remove this, and now in addition to B going to U, I add a new rule. So I have B going to U, I also add A going to U. Okay. So we don't want unit. So these type of rules are known as unit rules. The fourth is shortening the right hand side. Okay. So, suppose I have something like A going to U1, U2, U3 up to some UK, where let us say that K is greater than or equal to 3. Okay, so, if I have a long right hand side which is 3 or more, what I do is that I just shorten it in steps. So, first I add a variable, let us say A1, and I add the rule A going to, so basically A1 let us say is going to U1, U2. Okay, so A is going to U1, U2, and now I add the rule capital A going to A1 followed by U3 up to UK. Now note that this rule has only 2 symbols on the right hand side, and this rule has k minus 1 symbol on the right hand side. So, I have reduced it by 1 by adding one extra variable, and I keep on doing this until and unless k becomes equal to 2. Okay. And the last step of the algorithm is to make sure that there are only, so add so adding necessary variables. For example, let us say that I have a rule of the form A going to some uv, okay, where let us say without loss of generality u is a terminal symbol. Okay, so u is not a variable. What I do is that I add a variable, let us say capital U1, and I add the rules A going to U1 V and U1 going to small u. Okay. And if V is also a terminal, I again do the same thing. I add a new variable and I have A going to U1 followed by that new variable, and that new variable goes to V. Okay. Because recall that in the end I have to ensure that if I have a production rule with 2 symbols on the right hand side, it must be a concatenation of variables, and if I have one symbol on the right hand side, it must be a terminal. Okay. So, this is why we have to ensure this. Okay. So, let us look at an example to understand this more clearly. So, basically this is the algorithm. Now, let us look at an example. So, let us say we start with a context free grammar S going to A S B, A going to small a, capital A S capital A, or small a or epsilon, and capital B going to S small b capital S, or capital A or small b. Okay. So, we have a grammar which has 3 variables S, capital S, capital A and capital B, and it has 2 terminals small a and small b. How do I construct a Chomsky normal form grammar out of this? So, first what we will do is that observe that I have S on the right hand side of several rules. So, I have to get rid of that. So, I will add a production rule S naught going to S, and now I just have the other rules as they are. So, I will have S going to A S B, I have A going to A as A or epsilon, and I have B going to S B S or A or BB. Okay. So, this is our new start variable, and this does not occur on the right hand side of any rule. Our next job is to remove epsilon transition. So, I have an epsilon transition from A going to epsilon, and I have to remove this. So, then we have to find out every rule such that A occurs on the right hand side of that rule. I have one rule over here, I have one rule over here, and I have another rule over here. Okay. So, if there is a rule of this form where A occurs on the right hand side of a unit rule, I will add. So, if I remove A, basically I will get B going to epsilon. So, I will add B going to epsilon unless I have removed it earlier. Okay. So, please keep this in mind. So, let us go through it. So, first I remove A going to epsilon. So, I will have S naught going to S, then I will have S going to A S B. I remove A, so I get S B also. Then I have A going to A S A or A. I have removed epsilon, but I have to add the new rules. So, for this I will get now A S A or A capital A S, or if I remove both the occurrences I get A and capital S. Similarly, for B I will have S B S or B B, and now if I remove this occurrence of A, I get B going to epsilon, and I add B going to epsilon because I have not removed it so far. Okay. So, let me underline the new rules that I have added. So, this is added now, this is added, this is added, this is added, and this gets added. Okay. So, now in the third step I remove B going to epsilon because this also has to be removed now. So, what we get is S naught going to S, S going to. So, I have a rule ASB where B occurs on the right hand side. So, I will have S going to ASB followed by SB. I remove this occurrence, I get AS, and also I remove this occurrence. So, I get just S going to S, which is redundant. Okay, so, S going to S does not make any sense. So, we do not care about it. So, that is all. Now, in the next step I have A going to A S A or A or A S A or A capital A S or we have A capital S, and finally, we have capital B going to S small b S or small b b. Okay. So, this gets removed. So, now that we have removed all the epsilon rules, I have to remove all the unit rules. So, what are the unit rules? I have my unit rule S naught going to S, I have a unit rule in fact, that is the only unit rule that I have currently. Okay. So, I have S not going to S, which I will remove. Oh, so I actually missed this one out here. So, when I was removing B going to A, so of course, I keep this B going to A. So, of course, this will be there, and I add the new rule B going to epsilon, okay, and the same thing happens here also. So, I have, so when I, yeah, okay, so when I remove A going to epsilon, this is what should be there. Okay, so let's so removing S not going to S. So what we get is we remove S not going to S, and we get S so every occurrence, if I remove S not going to S, for every occurrence of S that I have on the right hand side, I will be adding the following rules. Okay, so now we have to remove unit rules. So we remove the first unit rule, S not going to S. So what we get is wherever S occurs, I add this new occurrence of S naught. So I will have S naught going to ASB or SB, and of course then I have S going to ASB or SB, A going to AASA or ASA or AAS or AS, and finally we have B going to SBS or BB or so we also have AS over here. Or we have A, and now we also remove the unit rule B going to A, and so finally, so what we get is if I remove B going to A as well, whenever I have A going to something, I add the rules of B. Okay, so if I just write it in one step, so I will have AS and I will have B going to SBS or BB, AASA or ASA or AAS or AS. Okay. So I have removed both S naught going to S and B going to A. Okay. So now that I have a rule which does not have any epsilon rules or unit rules, I will shorten all the rules on the right hand side, and I will add appropriate variables to complete them. So let me write down the final grammar. The final grammar will be something like this. So I have S naught going to, I have a new variable B SB or AS, S going to once again U1B SB AS, A going to U2A U3A, V1, U1, V1S or small a, B going to U4S, V2, V2 or U2A or U3A or V1, U1 or V1S or A. Now, I have these new rules for U1, U1 going to AS, U2 going to V1, U1, U3 going to V1S, U4 going to S, V2 and V1 going to A and V2 going to B. Okay. So, this I get by shortening. So, I add appropriately new variables and I get this. So, this shows that any grammar, any context free grammar can be converted to a grammar in Chomsky normal form. So, I will stop here. Thank you.